Welcome to class meeting 25 of the Introduction to Optimization. The announcements are the same. There is homework 5 already assigned and downloadable from the home page. And there are, I remember, 3 additional problems that are all proofs. 2 of them are found in the textbook. 1 you need to prove yourself. Okay, and it is due. Homework 5 is due on next Monday. Oh, okay. One more. Wednesday, 23rd. Is it? 24th? 24th. Right. So, the Wednesday class will be moved to Tuesday night. Yeah. What time? Yeah, 8 p.m. Okay. Yeah, but anyway, you know that all the class meetings are recorded, so yeah, you can. It's okay if you don't appear. Okay. Anyway, so from last time we started to study the constraint optimization problems, and we used lecture notes by Boyd and Vandenberg. The key words were Lagrangian something. So first, given a minimization problem, we consider standard or minimization problem. So we want to minimize function f. But here I adopt the notation from this lecture note. So f sub 0 is our objective function. Again, our parameter to be optimized is an n-dimensional real vector, and subject to inequality constraint and equality constraint. So here you can say that the explicit constraint is given by the set of n-dimensional vector n such that f underscore of x is greater than or equal to 0 vector, which means that each component function of f underscore is greater than or equal to 0, and h underscore of x equals the 0 vector. So this is the explicit constraint set. Of course, we have our constraint set omega given by the explicit constraint intersected with implicit constraint. Here, implicit constraint is all related to the domain of the objective function and domain of the inequality constraint function and domain of the equality constraint function. Because anyway, x must be a vector that can evaluate these functions. Okay. So given that, the Lagrangian is defined by what? By a kind of high dimensional function. So we introduce more variables than x. What kind of variables? Not only x, but also we introduce lambda and nu such that this function is the summation of the objective function plus lambda transpose f underscore of x. So be careful. This is scalar valued. This is vector valued, but now it becomes scalar valued because the length of f is the same of that of lambda. So, and we introduce nu that also makes the third term a scalar. Got it? So what if, for example, there is no equality constraint? Then we don't need to introduce this term. If there is no inequality constraint, this term disappears. For example, if we have f greater than or equal to 0 and h greater than or equal to 0, what do we do? Of course, we can define a new function that has this f as the upper part and h as the lower part, or it's still okay, right? But the difference is this. We intentionally restrict our lambda to be a vector whose components are all non-negative. Why we do this? Because we are going to use this L function in order to find the lower bound on our optimal objective function value. I will tell you in the next page anyway. So this is important. Now, given this definition, what was the most important property of this Lagrangian? First, is this correct? Is this correct? Of course, we need more. Now, is this correct? Is this inequality correct? So, you need to replace this L with its definition. What is it? f0 of x plus lambda transpose f of x. Now, if x is feasible, what does that mean? It satisfies that f underscore of x, let me see, was it less than or equal to or greater than or equal to? No. Here, yeah. By convention, we adopt this convention, right? We adopt this convention. F less than or equal to 0. Okay? So let me change this again. Yeah, we need to be careful. By the way, sometimes it is convenient to have inequality constraint function greater than or equal to 0 sometimes. In that case, what do you want to do? You want this lambda vector less than or equal to 0 vector when we minimize the objective function value. Sometimes we want to maximize some objective function value. In that case, probably what you want to do is to find an upper bound. In that case, depending on this sign, probably we need to change the sign of this, direction of this inequality. Got it? So even though we follow this convention, you must be able to adapt to different cases. Got it? For the minimization, we find a lower bound. For maximization, we want to find an upper bound by defining the Lagrangian. This is very important. Okay. So let me also change this part. Okay. So now, is this correct? Yeah, obviously. Now, what do we do? Now, this is the first property. Second property is this. So this is for general x in omega. Now, let's solve the left-hand side. What does that mean? We minimize f0 of x such that x is in omega. So, minimize f0 of x where x is in omega. Then what happens? Of course, this holds, right? So, we may say that here, of course, assumption is that lambda is greater than or equal to 0. Am I right? It's kind of obvious. Okay? You view the right-hand side as a function of x given fixed lambda and nu, where nu satisfies this condition. So you have two functions. One function is here, the other function is there. So for any point of x, this inequality holds. Then what will happen? If you minimize, right, of course, the minimizer for this one may be different from minimizer of this one, right? Got it? The minimizer of this problem, it may be different from minimizer of this problem. But still, inequality holds. Kind of obvious. Now, third property is this one. So, now, this side, the right-hand side, stays there. But now we introduce another inequality. Here, you may wonder why we have inf here. But if it bothers you, you may say that this is minimizing. Okay? Anyway, the idea is this one. You have the same objective function of x. Got it? L and lambda and nu are fixed given parameters satisfying this condition. Now, this omega prime is a bigger set than omega. Then in minimization, what happens? There is a possibility that you may achieve a lesser objective function value. That's why we have this. Got it? Unlike our lecture note, okay, where for omega prime, the authors of that convex optimized textbook just use D, that is the intersection of domain of the objective function, domain of the inequality function, and the domain of the equality function. But actually, this holds for any omega prime satisfying this property. So sometimes you can be more flexible in kind of performing this infimization. So remember that. That's the difference between this lecture note and my lecture today. This choice is perfectly good. I'm not saying that this is a bad choice. What I'm saying is that we may be more flexible as I started today's lecture. Got it? Now, let's define this function under this constraint and this one. Got it? And define this one as a function of what? Lambda and nu. Because if we choose different pair of lambda and nu, we will have different value, different minimum value or infimum of this. Got it? And this is called the Lagrangian dual function. But I want to change this d as a. Why? Because this function is not unique. It's not uniquely defined because we have flexibility in choosing omega prime. Got it? It is very important to choose omega prime so that we can obtain a lower bound easily. Sometimes any choice does not give us a good lower bound. But anyway, so now what do we have? Let's say this left-hand side as P star. Let me delete this point, right? Because in the beginning, I said min dot means minimize. Min means minimum, okay? So in order to have these inequalities, we have to have minimum and infimum, not minimize, infimize. So minimum of F0 subject to x in omega is now, let's see here, g of lambda nu for lambda greater than or equal to 0. And this holds for all lambda and nu. Am I right? So here what we have is max lambda nu and remove this. Got it? And we call this maximum value as d star. The reason why we use P and D is that we call this problem of minimization is the primary problem, the original optimization problem. And we call this maximizing g of lambda nu is the dual problem. So this D means dual. Got it? So what do we have? If P star and Q star are finite, we can always say this. And actually, interesting thing is this. What if P star is negative infinity? In that case, usually this is infeasible. What if this is plus infinity? This is infeasible or plus infinity or something. Got it? So anyway, so this holds. That's what you need to remember. Now let's see some examples from the lecture note, and it's very interesting. The first example is the least norm solution of linear equations. Here, this is the constraint. So we have a kind of hyperplane, or how do you say that? Intersection of hyperplanes, actually. And what is this one? This is 2 norms squared, right? So distance from the origin to the point in X. So it's like in 2-dimensional problem, you have some constraint set. Let's say this is AX equals B, and among these feasible points, you want to find what? Find that point that has the this is not the optimal point. Okay. Let me see this one, right? So this point, you want to find this point that has the minimum distance to the origin. Got it? Two norms squared subject to AX equals B. Of course, in order to have non-empty constraint set, definitely B is in the range of matrix A. Right? Yeah. This problem is actually very important. If you change this norm, probably you've learned some different definitions of vector norms. For example, what is this infinity norm? What is the infinity norm? Infinity norm is this. Among the components of X, the maximum of the absolute value of the components is the infinity norm. So you may define as this: max xi, like this. Got it? What is one norm? What is one norm? A sum of absolute values. Yeah. Yeah. What is zero norm? Right, number of non-zero entries. Components. So by changing the norm, you have different kinds of problems. Okay, among them, actually, this is the easiest. Anyway, by the way, what is this? This is a very special case of quadratic programming problem. So you have a quadratic objective function. Because what is this? X transpose identity X, right? And you have equality constraint given in this form. And probably you don't know how to solve it yet. Okay. Now, suppose this problem or some other similar problem is given as our primal problem. And suppose you don't know how to solve this problem, or you want to know possibly your numerical solver generated a close to optimal solution. Probably if you can find the D star, that is the optimal objective function value of your dual problem, it may be very, very useful for you to claim that your numerical result is close to optimal. Right? So let's formulate a dual problem. So this is P, and let's formulate D. But as you know, we need to define the Lagrangian first before we find G. Okay? So what is Lagrangian? Here we don't have inequality constraints, so let's introduce nu only. So here goes our objective function, And we may use ax minus b or b minus ax. It doesn't matter. Our lecture note has this ax minus b. And since this is the equality constraint, we don't need to restrict nu. Well, that's good. So this is totally an unconstrained function of x and mu. Now, we want to minimize this function of x. Let's assume nu is a constant. And what happens? We know that this is a quadratic function. Right? So this is the identity matrix. So this is the second order term, and this is the first order term, and this is constant. Now we don't know yet how to solve a quadratic programming problem, but we know how to solve unconstrained minimization of a quadratic function. Moreover, this says what? This says all positive, strictly positive eigenvalues. That's good. We have unique minimizer. How can we find it? By differentiating or by taking the gradient of this function over x. So sometimes some books put subscript here at right below of this grad sign. Okay, so this is partial derivative with respect to x. Then you know that this is 2x, actually 2ix, right? Plus A transpose nu. And what? Our minimizer of this function satisfies what? This equals 0 from the first order necessary condition. So what does that mean? Am I right? Yeah. Now, you may not happy with my use of star, okay? Because it looks like the primal optimal solution. So what do I do? This star. Okay. It's all up to you. Okay. Let's use this star. Okay. Now we plug this in to this function, because what do we want to do? We want to find g of nu, right? So what is our g of nu? So if we plug in, the first term becomes 1/4 nu transpose A transpose nu, and second term becomes minus 1/2, same thing. Am I right? And minus nu transpose B. So it looks like negative 1/4 nu transpose A transpose nu minus B transpose nu as a function of nu. Am I right? And now, what is this one? This is a quadratic function again. And what is this symmetric function? This is always positive semi-definite, right? Because it's a Lagrangian of A transpose. So this function is what? This function is a concave function, looks like this, in 2 or 3 dimensions. Now, maximization of this one with no constraint on nu will give us D star. Okay? So And this is what? This may be done very easily, especially when A transpose is invertible. Just a unconstrained quadratic problem. So, what can you say? If you find, okay, so what can you say is this. First, you may say this. Got it? So the primal optimal value is lower bounded by this one for any nu. Okay? What does that mean? You may arbitrarily choose nu. Of course, you want to kind of maximize this lower bound. So if you can solve this one, you can find a better lower bound. Got it? By the way, one of the property P star is greater than or equal to D star is called what? The weak duality. Okay? So this is called the weak duality. Sometimes so-called the strong duality holds. What does that mean? In that case, P star equals D star. We will see today the condition called Slater's condition, but sometimes Slater's condition that is a sufficient condition for the strong duality to hold. But suppose you cannot maximize, but you have this one. And somehow you evaluate the original problem. For example, by guessing X optimal. Then what will happen? What does that mean? You find a feasible X that satisfies condition, and you evaluate its norm square. Now, that is greater than or equal to P star, right? So if you choose arbitrarily feasible X, then you have this one, right? Now, somehow you evaluate this one as some nu, and if they are the same, then what can you say? That X feasible is optimal. Got it? So lower bound, finding a lower bound in a minimization problem may be, I'm not saying always, may be very, very powerful and useful. Got it? So this finding a lower bound is important. That's what I want to say. That's why this duality is discussed in many optimization problems. Now, let's see the next one. Now we have a LP problem, and we have a minimization of C transpose X, and X is in the first orthant, and we have equality constraint AX equals B. So we call it a standard form LP problem, right? Now, the reason why I did not delete this one is this. Our original lecture note by Professor Chong has one chapter all related to duality of a linear program. Okay. I like that, but this is better because this page explains derives the dual problem in a kind of bigger set. Okay, we have a general duality property, and we see the dual problem of our original standard LP problem as a special case. But by deriving this one, we see something interesting. That's I already actually emphasized. Okay. Now let's take a look at this carefully. Okay. So for the Lagrangian, we first have what? Objective function. Now we have what? We have inequality constraint, but what happens? If we want to keep x, then we must introduce lambda that is all what? Because we want to find the lower bound, right? If this is positive in a feasible set, we want lambda all negative, right? But there is another way. We still keep lambda all positive, but we subtract. Got it? That's what I told you. The reason why we do this, see that? Where is lambda? Yeah, anyway, they didn't explain. But anyway, here the importance is that lambda is greater than or equal to 0. Got it? So please write down here. Lambda greater than or equal to 0. Otherwise, this formulation of Lagrangian does not make sense in our minimization problem. Now, we have our equality constraint. So we have mu transpose and ax minus b. Got it? So we have this one with lambda greater than or equal to 0. Now, let's factor out this x. Okay? Then we have mu transpose minus b. So here. All the others are what? A vector times x. Got it? So far, no problem. Okay? The key is that there are many ways, but here we introduce all non-negative lambda and subtract it from the objective and equality constraint, scalarized equality constraint. Now, we want to what? We want to minimize this Lagrangian with respect to x. Right? But there are many options. Here, we just minimize this one without any constraint, infimize this one. You remember when we find the Lagrangian dual function, we just need to use a bigger set, any bigger set than our feasible set. So here the author puts no constraint. Got it? Or actually, you can start from the beginning that you remove this one and minimize this one over x greater than or equal to 0. Got it? Because what? Because we want a lower bound. Okay? But anyway, so let's follow their logic. So here, so far so good. Now, what happens? The problem occurs here. X can have any vector. It could be very, very, very large, one of the components. Its magnitude could be very, very large. Now, what happens if this vector is not 0? Since your infimization is what? Your infimization has no constraint. It's like this. In one-dimensional problem, this is a constant and you multiply x. Okay, so let me give you. So let's simplify. Suppose you have L of some x. That looks like Cx, let me see, minus B nu. Something like this. What is this? When lambda and nu are given and x can be any value. What is this one? As a function of x, it's a straight line. Am I right? It's a straight line. Depending on the sign of this part, this is the slope. You may have something like that or something like that. Am I right? Now you don't have constraint. What will happen? When you infimize this one over x, there is only one case with which you do not end up with negative infinity. What? This is 0. If slope is 0, then you have minus b nu, a constant like this. Am I right? But if this slope is not 0, then infimum of this one over x is always negative, regardless of sign of this one. So exactly same logic applies here. So be careful, this is 0 vector. If I were you, I will put underscore here. Because the authors are they are familiar with this. But this is actually 0 vector. Got it? A transpose nu vector minus lambda vector plus c vector is 0 vector. In that case, this is minus b transpose nu. So you have infimum of L is given by minus b transpose nu. Otherwise, if this is not a 0 vector, then its infimum is negative infinity. Now, which one do you want to choose? Here, actually, you can choose anyone. Because this negative infinity anyway serves as a trivial lower bound in your minimization problem, right? In your prior problem, you want to minimize objective function subject to your constraint. Anyway, negative infinity is always a lower bound. So I'm not saying that this is useless. I'm saying that in this case, this is useful. Got it? I'm not saying this otherwise case is useless. I'm saying that in this case, this lower bound is useful. Now, what can you say? You say that the primal optimal value P star is lower bounded by this one. When? Under this condition. But you may say that, wait a minute, where is my lambda? Actually, you've seen exactly same problem in the midterm 2. How can you see this? How can you view this lambda? You can view this lambda as because this is all non-negative, is a slack variable. Anyway, your objective function does not have lambda. So you can remove lambda and make this equality to inequality. Right? You've done this. Okay? Actually, the reason why I put that problem is for this one. So, what do you have? You have a new lower bound under this condition. But what if you want to have a more tighter lower bound? You want to maximize this objective function value. Or you want to minimize without this sign. Then what is this? What is this as a problem of lambda? It's again a LP problem. Right? So, one observation is this. Given our standard form LP problem, the dual problem is also an LP problem. Right? And it's given like this. Now, this is one way to derive our, here, of course, you need to write your LP problem here, derive a new LP problem. But there is another way to end up at the same result. So, let me give you this. Suppose you just define your Lagrangian like this. But here, instead of introducing lambda, you just say that, okay, x is greater than or equal to 0 as our original primal problem requires. No problem, actually. As I told you, Lagrangian Lagrangian dual function are not uniquely defined. It's just for your convenience. The definition of Lagrangian is that you kind of find a function, new function in a higher dimension, so that you have your objective function and you have equality constraint functions weighted sum and inequality constraint functions weighted sum or sum of them, so that anyway you find a lower bound. Got it? So as far as you can find a lower bound, it's perfectly okay. You don't need to put minus lambda transpose x and assuming lambda greater than or equal to 0. As far as it's okay, it works. Now consider this problem. Oops, what's going on? Okay. So I may define G of nu as infimum of L x nu where x greater than or equal to 0. So let me ask you a question. Can it serve for any nu? Can it serve as a lower bound of P star? Can it serve? Yes. This always works. Am I right? So it's okay, perfectly okay. Depending, be careful, depending on your choice of nu, the optimal x star for your primary problem and optimal x may be different. Okay? But still this holds. Now let's carefully analyze what's going on. So you have infimization of C transpose X plus nu transpose Ax minus B. And again, we can reorder this part like minus nu transpose B plus, what was that? C transpose plus nu transpose A. Be careful, no lambda here, right? X. Got it? But here we have constraint on X. This must be carefully noticed. Now, again, what is this? What is this? In one dimension, this is a straight line. Almost the same argument as this one. But there is a difference. What is the difference? Now, suppose this is 0. Then what happens? For any x, this is 0. So your lower bound is minus nu transpose B. Now, what about this is positive? So it's kind of increasing. Now, in your minimization, actually, no problem, right? What if this is negative? Then you have a problem, right? So first, what you know is that this one must be greater than or equal to 0. Am I right? Under this constraint. But that is for one dimension. Now, for 2, 3, 4, 5 dimension, what will happen? What you need is that this holds. By component, this is all non-negative. Right? What happens if one component is, need to be careful, need to put transpose here. What if one component is negative? Then for that component, you can make x arbitrarily large so that this becomes negative infinity. Okay? So you have this one. Got it? So similarly to what we just have, we have this minus nu transpose B if C transpose nu transpose A greater than or equal to 0 transpose, and negative infinity otherwise. Then what can you say? You say that P star is lower bounded by minus nu transpose B under this constraint. Now, you want to maximize your upper bound, a lower bound. What happens? Maximize this one subject to that. And it turns out it's exactly the same as we already have derived. Got it? By introducing lambda. So what I want to say is this. Formulating the Lagrangian is not unique. Okay? Deriving the Lagrange dual function is not unique. Okay? It's all up to you. Got it? Your objective is to linearly combine the sum or all of the constraint, equality and inequality constraint functions so that you have a good lower bound. And even what you want is that you want to maximize the lower bound so that we have a tighter lower bound. Got it? So this is very important. Otherwise, you will get confused every time you will see Lagrangian function and Lagrangian dual function. Okay, anyway, so let's see the third example. Oh, by the way, the first example and second example, actually, they have, when our dual problem is solved, they satisfy the strong duality, interestingly, when the problem is feasible. Now, the third one is the case where we have no strong duality. So in this case, only weak duality holds. And let's take a look at the problem. This is called two-way partitioning because of our one way of interpreting this problem. But we confront very similar problems in many cases, especially those signal design research. For example, if you take Professor Yang's signal design course, you will see something similar to that. Of course, you will not solve the problem like this. You will probably use the property of a finite field so that you have a very good solution. But anyway, so here, all the components are real. Here, W is a square matrix, but not necessarily symmetric. But anyway, so you have X transpose WX, but you may assume that W is symmetric, as you know that only the symmetric part of W will remain after you compute that. Anyway, here X can be 1 or minus 1. Okay? Even though this looks strange, you say it says that X is 1 or minus 1 because X is real, Xi is real. So actually, this problem is not a continuous optimization problem, but a discrete optimization problem that in the beginning we decided not to handle at all. But anyway, this duality can be applied to the discrete optimization problem. Now, you want to find vector x consisting of 1 and minus 1. And want to find such vector x that minimizes its value. This one may be an approximation of peak to average power ratio, for example. For example, in my lab, one of my research assistants solves very similar problem like this. He wants to minimize the peak to average power ratio of DFT spread or FDM something by Pearl shaping. So this corresponds to Pearl shape. This W includes the other parameter for the Pearl shaping, and X is data. But in his case, of course, X is complex value, then it could be QPSK or some other thing. But anyway, usually this kind of problem requires what? Exponential complexity. You have only one way, okay? That is the exhaustive search. If the length is very large, what happens? If this length is n, the complexity is 2 to the n. Of course, 2 to the n minus 1 because due to the symmetry or something. But anyway, of course, if W has a strong structure, you can reduce the complexity. But in general, this has exponential complexity. It's an NP-hard problem. Okay, if you want what is NP-hard, look up the algorithms textbook. Okay. Also, I strongly recommend that if you want to become a PhD, formulating some algorithm, sit in the algorithm course offered in computer science and engineering department. Anyway, you need to somehow expose to that adaptive algorithm or any algorithm. Got it? Because you can learn some formalism in describing the algorithms or in describing the complexity of the algorithms. So it may be very useful. Okay? So use POVIS and you officially click that sit in radio button and really sit in. Okay? Then your professor cannot kick you out. Okay? Otherwise, your professor say that, oh, who are you? And go out, something like that. Okay, anyway, now the optimal X has some components 1 and some components -1. So you can view this as a partitioning into two groups. That's why it's named as two-way partitioning. For example, if this problem is a X Hermitian transpose some Hermitian symmetric W and X, and this is X sub I of absolute value of X sub I equals 1, or Xi is a QPSK cancellation, then it could be four-way partitioning problem. But anyway, so this optimization cannot be solved in the in a linear or some non-exponential, sub-exponential complexity. But interestingly, dual problem can be solved easily. So let's see how to formulate a dual problem. Since we have equality constraint functions only, we introduce how many? N dual variables for the equality constraint. So here they are nu sub i's. Got it? So we have our objective function and weighted sum of equality functions, right? If we move 1 to left hand side, x sub I squared minus 1 is the equality function. Got it? Now, this can be viewed as this quadratic problem, quadratic infimization problem. Am I right? And now be careful. We can just assume that W is symmetric. Here, is there any other constraint? No. Now we have diag of nu. By the way, this nu is a vector. So diag nu is to what? Transform this vector to a square matrix whose diagonal entries corresponds to the components of nu. Okay, that is standard notation as you use in MATLAB. Now, this is the matrix for the quadratic problem. Okay, actually, as you see that there is no x here. So as far as this quadratic matrix, square matrix has all what? All positive eigenvalues. You can say that the infimum is this one, because infimum of this one is 0. But if at least one of the eigenvalues is negative, what will happen? Then we have negative infinity for that. Right? By the way, that constraint, W plus diag nu, has all non-negative eigenvalues. That condition is same as this condition. You can show that. Okay. Anyway, I may put it as a homework. It's a linear algebra result. So what happens? You have two cases, trivial lower bound and non-trivial lower bound. Let's use non-trivial lower bound. And non-trivial lower bound says that the primal optimal value, P star, is lower bounded by 1 transpose nu. What does that mean? Summation of nu sub i's times -1. If this holds. So what can you do? You may maximize this problem. So you may formulate a dual problem of maximizing -1 transpose nu subject to this condition. And you may say that, this problem looks more difficult. Actually, you are right. Solving this problem directly may be formidable because now you have this strange condition. See that, what does this mean? This is a matrix. So this means positive semi-definite. Right? You may say that, how can I solve? But as I told you, under this constraint, any 1 minus 1 transpose nu can serve as a lower bound. So still this may be useful as far as we find good, means large value of this one. Right? And one example is this one. We just choose, for example, lambda vector as what? The minimum eigenvalue of W times or 1. And you take the negative value. Then you can easily show that this holds. Okay? In that case, you can find this one is what? You plug in here and you have n times minimum eigenvalue of W as one lower bound. I'm not saying that this is the best lower bound given our dual problem. I'm saying that this is one straightforward lower bound. Got it? So, I believe I've done this already, right? Yeah. Anyway, so far we derived the lower bound and some condition. And as I told you, just we want to find the best lower bound by maximizing this lower bound. That is the dual problem. So we maximize our Lagrangian dual function subject to over lambda and nu subject to lambda greater than or equal to 0. Because why? Because we have our original problem is minimization. We want to find the lower bound, so we want to subtract something. But our inequality constraint function is all negative under feasibility, so we have plus lambda transpose f underscore. That's why we have lambda positive here. If we have subtracted, then probably we have lambda less than or equal to 0. Got it? So this is the dual problem. And here comes a new definition. Sometimes we call lambda and nu pair is dual feasible if it satisfies, it's feasible to this dual problem. Okay? Because here dual problem requires lambda nu greater than or equal to 0. Okay? And of course in the domain of G function. And this is the example I just told you, right? You should remember that there were two ways to end up with the same dual LP problem for this standard LP. Right? We introduced lambda and nu and end up with this one by viewing lambda as a slack variable, or actually a slack vector, or we just removed that inequality, but when we infimized over x greater than or equal to 0 and ended up with here. Okay, seems it's very, very slow, but anyway, let me keep doing that. This is what I already explained. For any case, if we have defined our Lagrangian function so that if we infimize that problem over some omega prime, we have a lower bound, then this always holds because we intentionally designed the Lagrangian function and defined the Lagrangian dual function and dual problem. So this always holds. That is called weak duality. And if this condition holds, if this holds, we say that the strong duality holds, given the primal problem and dual problem. And the first and second one satisfies strong duality, but the third one didn't. By the way, for the third one, we had this problem, right, as our dual problem. We want to maximize minus or 1 vector transpose mu subject to this matrix is positive semi-definite, right? Now, here goes a sufficient condition for the P star and D star are the same, which means that this is a sufficient condition for the strong duality to hold. Got it? This is not the necessary and sufficient condition, but this is a sufficient condition. So, for example, you check whether your primal dual problem satisfies this one. And this condition is satisfied. Then you can say what? Okay, strong duality holds. Got it? Let me see why this looks different. Okay. Yeah. Slater's constraint condition is, I told you, sufficient condition. What does that mean? We do not talk about general constraint optimization problem with some inequality constraint function and inequality constraint function. The Slater's condition requires this one. Got it? Got it? And also convexity. Because this lecture note is for what? Is for convex optimization. Okay? So F0 is convex and Fi is convex. And here equality constraint function is what? Affine, Ax minus B. So this is very special. But in this case, if this means interior of domain, okay? Means that you remove the boundary. Got it? So you remove the boundary of the domain of these functions, and also boundary defined by this inequality constraint function. But not for this equality, because you cannot remove. If this is not, then infeasible, right? So it's kind of a subset of your constraint set, but your boundary removed. You can just understand that. And if that set is not empty, okay? If that little bit smaller set than omega is not empty, then what? This convex optimization problem has strong duality. Got it? Okay. And now let's apply this one to our linear programming problem. Now we have inequality form Lp. Of course, there are many inequality form Lp, but here we want to minimize C transpose X. And what's the difference? Here is inequality, and we don't have first orthant constraint. Got it? Now, given that, we can just introduce lambda as our dual variable, and we infimize this plus lambda transpose Ax minus B. Then you have minus B transpose lambda if this is 0, and minus infinity otherwise. Now you derive very fast, right? And the dual problem is definitely maximize this one subject to this equality constraint. But here be careful, lambda must be what? Greater than or equal to 0. So we have additional constraint. Now, what about the constraint set? Domain of objective and equality functions is everything, R to the n, right? So as far as removing this equality, so you have Ax less than B vector is not empty. This satisfies Slater's sufficient condition because linear function is a convex function, very special. It's convex and at the same time concave. And this one, what? This is kind of consists of intersection of half planes, right? So you understand component by component. What does that mean? Let's say that first row times X vector is less than B1. That is what? That is half space, right? You have a plane, hyperplane, and either the part including origin or the other part are all feasible. And you intersect them, and you have a convex function, convex set. So this is, if this is not empty, okay? So if there exists any X tilde satisfying this condition, then it satisfies Slater's constraint qualification or Slater's sufficient condition. So strong duality holds. Got it? What else do we have? We have quadratic programming problem. And this is more difficult than we've just seen. At that time, we have X transpose IX and AX equals B. Now we have a little bit different form. By the way, here P is a given parameter, but S means it's symmetric. N means N by N. Plus means positive definite. If you have just plus, it means positive semi-definite. Got it? So P is N by N, symmetric, positive definite matrix. So without constraint, what is the minimum value? 0. But since you have a constraint, the minimum value may not be 0, right? As I just told you, if this is not empty, this is what? This is a convex set defined by the intersection of hyperspaces, half spaces. Anyway, definition of half spaces and other things appears of the lecture note and the textbook convex optimization. I'm not going to ask you that concept in this course. Anyway, so dual function consists of objective, and you introduce dual variable lambda for the inequality constraint, and it's very simple quadratic function of lambda. And A P inverse if you infimize, you will end up this one. So you solve this quadratic problem because P is invertible. So you have that one. Now dual problem is given by this one. Just copy your lower bound and put the inequality constraint for the dual Lagrange multiplier or dual variable. And if this has none, if this set is not empty, then this dual problem and the primal problem has what? P star, D star the same. So strong duality holds. Why? Because this is a convex function defined on a convex set. So Slater's condition can be applied. What else do we have? Oh, by the way, as I told you, Slater's condition is a sufficient condition. For what? For standard convex optimization problem with equality constraints. Equality constraint function is affine. Okay? But we may have other conditions for non-convex problems, right? And I'm not saying that only for convex problems this strong duality holds. For non-convex problems, sometimes strong duality may hold. For example, in this problem, where A is not positive semi-definite. See that? A, without this slash, A is positive semi-definite. This means A matrix is not positive semi-definite. So this may have a saddle point, right? And what is this? This is the inside and the boundary of a sphere. Am I right? Now you want to minimize that. And your problem can be easily derived under some condition. So you have your dual problem like this. Okay? It's not that difficult to obtain. Interestingly, even though I never mentioned, this problem can be converted to an equivalent semi-definite programming problem. And I haven't yet defined what is a semi-definite programming problem. But semi-definite problem. But anyway, it can be converted to that one. And this can be numerically solved. Got it? Anyway, you will learn in convex optimization course how to convert this problem to that one. Okay, I believe I'm almost done. Okay, it seems that this page takes a lot of hours. Okay, so let's continue next week. Okay, that's all for the day.